Okay, good morning. Class begins. Last time we have learned the beginning of the chapter 4 about medium access control sublayer. It is a sublayer of the data link layer, especially for broadcast channel. We will study these points. Channel resource allocation problem, multiple access protocol, Ethernet, wireless LAN, broadband wireless, Bluetooth, RFID, and data link layer switching techniques. Network links can be divided into two categories: point-to-point connections, or point-to-point links, and those using broadcast channels. Broadcast channels are sometimes referred to as multi-access channels or random access channels, usually applied in local area network. Broadcast channels usually lies in local area networks. So broadcast channel characteristics including multi-access protocols is important for local area network. In any broadcast network, the key issue is how to determine who gets to use the channel when there is competition for it. So in broadcast channel, we will focus on the protocol to determine who can use the channel when there is competition. The protocols used to determine who goes next on multi-access channel belong to a sublayer of the data link layer called the MAC sublayer. Here MAC means media access control. The MAC sublayer is especially important in local area network LANs, particularly wireless local area network, because wireless is naturally a broadcast channel. The central theme is how to allocate a single broadcast channel among competing users. So usually the channel might be a portion of wireless spectrum in the geographic region, or a single wire or optical fiber to which multiple nodes are connected. We will talk about two kinds of channel allocation techniques, static and dynamic ones. First, we will talk about the static channel allocation. Since although static channel allocation has many shortcomings, it is inefficient, but it is the basis of allocation technique. Traditional way of allocating a single channel such as a telephone trunk among multiple computing users, is to chop up its capacity by using some static allocation method, such as FDM, TDM, CDM, and WDM, etc. If there are n users, the bandwidth is divided into n equal-sized portions, with each user being assigned one portion. Since each user has a private frequency band, there is now no interference among users. There is no competition. There is no interference among the users. But the bandwidth is divided into n equal-sized, and each user has its private frequency band. So when the number of senders is large and varied, we know some senders, if there are n users, I think not all of the users is sending. Some of them probably has no data to send at some moment. So the number of senders is large and varying, or the traffic is bursty. The traffic is bursty means sometimes it has much data to send. Sometimes they have no data to send. That means bursty, varying. So when the traffic is varying or bursty, then the static channel allocation, such as FDM, TDM, etc., presents some problems, presents some shortcoming. If the spectrum is cut up into n regions and fewer than n users are currently interested in communicating, a large piece of valuable spectrum will be wasted. So if we divided the bandwidth into n equal-sized portion, but a few of them are used and others are wasted. So dividing the single available channel into some number of static sub-channels is inherently inefficient. So the static channel allocation is very easy and the basis of the allocation scheme, but it is not suitable to the dynamic environment. A static allocation is perfect to most computer systems in which data traffic is extremely bursty. That is why the static allocation is inefficient. Often with peak traffic to mean traffic ratio of 1000 with 1. Consequently, most of the channels will be idle most of the time. The poor performance of static FDM can easily be seen with a simple Queen theory calculation. A standard Queen theory result, we can get T equals, according to this equation. Here, the mean time delay denoted by T The data rate, denoted by capital C, bps, we assumed that the frames arrive randomly with the average arrival rate, lambda frames per second, and that the frames vary in length with an average length of 1/mu bits. With these parameters, the service rate of the channel is mu c frames per second. Mu, capital C, frames per second. Here mu is the length, the average length of 1/mu bits. And the data rate is C bps. So the service rate of the channel is mu c frames per second. And we can get the delay, the mean average, the average time delay, average delay of this system. Capital T is this. Here, then we analyze this situation when divide the single channel into n independent subchannels, each with capacity C over n bps. Then the mean input rate on each of the subchannel will now be lambda divided by n, right? Since the average arrival rate is lambda frame per second, now the single channel is divided into n independent subchannel. So the rate of each of the subchannel will now be lambda divided by n, lambda over n, right? So computing capital T according to Queen theory, we get Tn. Here n means when the channel divided into n subchannels. So Tn is the new capacity, new lambda, right? New lambda divided by n, capital capacity divided by n. So we get Tn, new T, is n times T. This result says when the channel is divided into n independent subchannels, the performance becomes better or worse. Becomes worse, not better, right? So the mean, because the delay became n times than before, so it is worse than before. The mean delay for divided channel is n times worse than if all the frames are somehow magically arranged orderly in a big central queue. So when divided into n independent subchannels, the performance becomes worse. Precisely the same arguments that apply to FDM also apply to other ways of statically dividing the channel, since none of the traditional static channel allocation methods work well at all with bursty traffic. We will now explore dynamic methods. Static will not be reality, will not be real protocols, since although it is simple than dynamic methods. Here we'll begin to talk about dynamic channel allocation design. Before we get to the first of the many channel allocation methods, it is worthwhile to carefully formulate the allocation problem. Underlying all the work done in this area are following 5 key assumptions. Assumption 1 is independent traffic. That means frame arrivals are independent, both across stations and at a particular station, and that frames are generated unpredictably but at a constant rate. The independent traffic, the frame arrival is independent. Assumption 2 is with single channel. Single channel is available for all communication. Why we assume there is a single channel, that it is different from the static allocation. Because in static allocation, a single channel divided into independent and independent subchannels. That is a static allocation. But now we talk about dynamic channel, dynamic allocation. That means we have a single channel totally bandwidth, but how to dynamically use them. So it's available for all communication. All stations can transmit on it. And we should adopt a specific protocol to determine which user can send data into the channel dynamically. Assumption 3, observable collision. Collisions can be observable by the stations. If 2 frames are transmitted simultaneously, they overlap in time and the resulting signal is garbled. This event is called a collision. All stations can detect that a collision has occurred. A collided frame must be transmitted again later. That no errors other than those generated by collision. That means if a frame cannot be, if a frame failed to be transmitted, that is not because error. It is the reason of collision occurs. Observable collision, we assume 2 persons talked with each other face to face. If they talk simultaneously at the same time, then there's a collision. Then one of the person or 2 found a collision has occurred, then they talked again. So a collision frames can be transmitted again later. Assumption 4, that is, time can be considered as continuous or slotted. Time may be assumed continuous, in which case frame transmission can begin at any instant. Alternatively, time may be slotted or divided into discrete intervals, called slots. Frame transmission must then begin at the start of the slot. A slot may contain 0 or 1 or more frames. Usually, a slot may contain 1 frames. If in this slot there is no frames transmitted, then contains 0. Because the data traffic is bursty, that means and most of the time the station has no data to send. So at the slot there may be 0 frames. 0 frame. Corresponding to an idle slot, a successful transmission or collision, respectively. Master assumption is carrier sense or no carrier sense. Okay, assumption 3 says collision can be observable, right? Can be observable. That means the stations can find the collision, know the collision if the collision occurs. Then the next assumption says carrier sense. What is the carrier sense? With the carrier sense assumption, stations can tell if the channel is in use. Is in use means if the channel is busy or some station one of the station is transmitting, there is traffic on the channel. So the channel is in use or busy when some station transmits its traffic on it. So stations can tell if the channel is in use before trying to use it. That means a station can hear the traffic, can hear the channel before sending traffic, hear from the channel before transmitting its traffic. So that means the carrier sense. Tell if the channel is in use before trying to use it. No station can attempt to use the channel while it is sensed as busy. Then if 2 persons talked with each other, if one person is saying, then the other one should listen to him, right? To listen, not to talk. That means if the channel is busy, then no station will attempt to use the channel. That is the content of the protocol. No station will attempt to use if the channel is busy. If there is no carrier sense, on the other hand, if no carrier sense, stations cannot sense the channel before trying to use it. This is an assumption. So assumption, that means the choice of the property, of the channel, or how to design, the assumption about how to design the protocol for the channel. So if there is no carrier sense, stations cannot sense the channel before trying to use it. They just go ahead and transmit it. If there is no carrier sense, even the channel is busy, but stations cannot sense. So the stations just go ahead and transmit. Then later, they can determine whether the transmission was successful. If they found the transmission is failed, then they transmit the frames again. But if there is no carrier sense, I think there's many conditions in the channel, more conditions than carrier sense, right? So this is the 5 assumptions: independent traffic, single channel, observable condition. But the last two assumptions, we have two choices: continuous snorted times, or carrier sense, or no carrier sense. This is how to design the protocols. That means it depends on the design of the MAC protocol. Design depends on MAC design. We can continuous time carrier sense, or continuous time no carrier sense, or snorted time carrier sense, or snorted time no carrier sense. We have 4 designs. They are different. Which one is better? We should do some experiment, right? We cannot determine which one is better. Usually, snorted time carrier sense is better than others. Snorted time with carrier sense is better than other 3 choices. To avoid any misunderstanding, it is worth noting that no multi-access protocol guarantees reliable delivery. Even in the absence of condition, the receiver may have copied some of the frames incorrectly for various reasons. Even in the absence of condition, even without conditions, the receiver may have copied some of the frames incorrectly for various reasons. The other parts of the link layer or higher layers provide reliability, such as we can use TCP or other reliable transmission protocols to guarantee reliable transmission end-to-end. For example, TCP can be used. Then we talked about Aloha. Aloha is the first broadcast dynamic protocols. Aloha, what is the assumption about Aloha? Independent traffic, single channel, observable condition, continuous, no carrier sense. No carrier sense. Aloha is no carrier sense. The basic idea of the Aloha system is simple, that no users transmit whenever they have data to be sent. Whenever they have data to be sent, then the users can transmit. That means no carrier sense, right? Before transmitting their data, they will not hear the channel. They will not tell if the channel is busy or not. So with no carrier sense, there will be conditions. Of course, the colliding frames will be damaged. In the Aloha system, after each station has sent its frame to the central computer, this computer rebroadcasts the frames to all of the stations. So the central computer is the machine to forward the client stations. So each station sends its frame to the central computer. Then the central computer rebroadcast, means forward the frames to all of the stations. Then the central computer works as the role of router or switch. This is the central computer. Then a sending station can thus listen for the broadcast from the hub to see if its frame has gotten through. If the frame was destroyed, the sender just waits a random amount of time and sends it again. The waiting time must be random, or the same frames will collide over and over in lockstep. So that is why sender waits a random amount of the time. If two machines send its frames simultaneously, if they wait for a same time, for example, all of them wait for 1 second, then after 1 second they send again, then the frames will collide again, right? So the period of waiting time should be random. The waiting time must be random, all the same will collide over and over. So then systems in which multiple users share a common channel in a way that lead to conflicts are known as contention systems. So Aloha system or Aloha Mac protocols deals with the basic problems for contention systems. Aloha also gives a basic idea for the design of Mac protocol. The first Mac starts out then okay, the first Aloha version, first version of Aloha is pure Aloha. Pure Aloha, that means usually adopt the first choice, continuous time. Pure Aloha adopted the choice of continuous times and no carrier sense. So pure Aloha is continuous time. Snorted Aloha is adopted the assumption of snorted times. So first we will consider what is the pure. The sketch of frame generation in the Aloha system in this figure 1. We have made the frames all the same length. This is an assumption. Just an assumption. Then because the throughput of Aloha system is maximized by having a uniform frame size rather than by allowing variable length frames. So if the frames has a uniform frame size, only in these situations, in this condition, the performance of the Aloha system can reach the maximum object. Okay, so whenever two frames tries to occupy the channel at the same time, there will be a collision, and boost will be doubled. Then, when two frames try to occupy the channel at the same time, that means at the same time there is more than one senders is transmitting. For example, user A, B, D are transmitting their frames. They have overlap in the frame transmitting time. Then at this period, two frames is collided. Then, in these conditions of pure Aloha, what is the efficiency? In other words, what fraction of all transmitted frames can be transmitted successfully, escape conditions under these chaotic circumstances? We can look at the conclusions. First, consider an infinite connection of users typing at their terminals. That means some users, a connection of users typing message at their terminals. Then if they enter the enter key, press the enter key, the message will be transmitted. A user is always in one of the two states, typing or waiting. Typing message and send out, or waiting for reply. So a user is always in one of the two states. That's the frame time. Frame time denotes the amount of time needed to transmit the standard fixed length frames. At this point, we assume that the new frames generated by the frames are well modeled by Poisson distribution with a mean of m frames per frame time. For reasonable throughput, we would expect n is between 0 and 1. Mean. That means there is an m frames per frame times. The minimum is no frames. That means during the frame time, the channel is busy, is idle. No frames transmitted. The maximum 1 means a frames is exactly transmitted per frame time. The channel is busy with 100% efficiency. Okay, let's have a rest for 10 minutes. Let's have a rest for 10 minutes. Please keep connection. Please keep connection. Rest. Have a rest for 10 minutes. Okay, let's continue. Last section, we have considered the pure aloha. About the pure aloha, we have some assumptions. We assume that new frames generated by the stations are well modeled by Poisson distribution, with a mean of n frames per frame time. Here n is between, in this range, 0 to 1. In addition to the new frame, the stations also generate retransmissions of frames that previously suffered collisions. Let us further assume that. So there are many assumes if we want to deal with real problems. So only we have many assumptions, we can deal with some real problems with some mathematical method. We should modeling the problems at first, right? So let's further assume that the old and new frames combined are well modeled by Poisson distribution with mean of G frames per frame time. Clearly, G is larger than N. G is larger than N. The throughput S is just the offered node. Is just the offered node. G times P0. Here P0 is the probability of a transmission succeeding. So the system throughput S equals G times P0. Here P0 is the probability that a frame does not suffer a collision. That means the probability that a frame is transmitted successfully, right? So P0 is a success probability. So G is S equals G times P0. What is the G? G is the mean of G frames per frame time. G frames are transmitted in the frame time per frame time. So if the successful probability is P0, then throughput is G, P0. Then what is the P0? Can we determine the value of P0? So we modeled the transmitting system with this figure. So under what conditions will the shaded frame arrive undamaged? The shaded frame arrive undamaged. Under what conditions? So if there is a frame here or here, then there must be conditions, right? So if the frame time we denoted by T denoted by t, and the beginning of the time is t0. And this is a time, the frame time is t, then the dashed line will divide the time into some slots, right? T0 plus t, T0 plus 2t, T0 plus 3t. We have 3 time slot, right? We have 3 time slot. Then let t be the time required to send a frame. So t means frame time, a frame time. If any other user has generated a frame between time t0 and t0 plus t, the end of that frame will collide within the beginning of the shaded one. Right? If any other user has generated a frame between T0 and T0 plus T, right? T0 and T0 plus T. That means the beginning of the frame is larger than T0 and less than T0 plus T, then the tail of the end of the frame will be overlapped with the shaded frame. So collision occurs, right? If the beginning lies in this range, then the end of the frame will lies in this range, right? So there is an overlapped. That is why we say if any other user has generated between T0 and T0 plus T, the end of that frame will collide with the beginning of the shaded one. That frame will collide with the beginning of the shaded one. Collided with the beginning of the shaded one, right? Then if the beginning of a frame lies, if the beginning of the frame lies in the second slot, T0 plus T and T0 plus 2T, there is also collision occurs, right? So in fact, the shaded frame's fate was already sealed even before the first bit was sent. But since impure Aloha system does not listen to the channel before transmitting, there has no way of knowing that another frame has already on the way. Similarly, any other frame started between T0 plus T and T0 plus 2T will bump into the end of the shaded frame. Will bump to the end of the shaded frame. So from this figure or this model, we can analyze the fate of the shaded frame, right? So we can calculate the probability of successful transmitting. The probability that key frames are generated during a given frame time in which G frames are expected. It is given by Poisson distribution. Probability key frames are generated keyframes are generated according to Poisson distribution. GK times E minus G over key. Right? This means key times key minus 1 times key minus 2 dot 2 times 2 times 1. This is the probability that key frames are generated. Probability of key frames are generated. So the probability of 0 frames is just E with the power of minus G. Why we consider 0 frames? Why we consider 0 frames? Because if there is a frame during this slot, or if there is a frame during the second slot, then the shaded frames will be collided, will not successfully transmitted. So we should calculate the probability of 0 frames transmitted in some time slot. Okay. In the interval 2 frames times norm, the mean number of frames generated is 2G. The probability of no frames being initiated during the entire vulnerable period is less than P0. P0. How can we get P0? P0 means P0. From this equation, we can get P0 equals what? Equals G with the power of 0, right? Times E equal, right? Here K is K 0 frames means the key is 0. So we set key this is 1, right? So this is 1. So get E is the power of minus G, right? So the probability of 0 key here, K equals 0, is E minus G. So in the interval 2 frames times long, 2 times long, the mean number of frames generated is 2G. The probability of no frames being initiated during the entire vulnerable period is less than E minus 2G. So using S G plus G times P0, S, so GS equals G times P0, right? So here we get P0 is E minus 2G. So S, the efficiency S equals G times E 2G. Then if we set X is G and Y is S throughput per frame time, we can get the curve of the relation between S and G, right? So we can find that when G is 0.5, the pure aloha reach the maximum throughput, right? Pure aloha. So we say look at the pure aloha. When G equals 0.5, then the probability, the throughput of pure aloha reached nearly 20%, right? Nearly 20%. Exactly this 18%, right? Nearly 20%. Exactly this one. So the maximum throughput occurs at G when G is 0.5, then S is about 0.184. In other words, the best we can hope for is a channel utilization of 18. It is not, the result is not very encouraging. It is not very good. But since there is no complex protocol is adopted, right? It's a very simple protocol designed for pure aloha. No carrier sense, right? Continuous times. That means time is not considered time slotted. So continuous is more simple than slotted time scanned. So this result is not very encouraging. But with everyone transmitting at will, means no carrier sense. Since no carrier sense, then we cannot hope for very high throughput, right? There must be many conditions in the system. In this contention system, there must be many conditions since everyone transmitting at will. That means can transmit at any time when we have data to send. We could hardly have expected a 100% success rate, right? So we might think that 18% is not very low. It's not the worst. It's not the worst, right? So that is the result of pure aloha system. Then from this figure, the result of the snorted aloha is also shown. Then how to analyze the performance of snorted aloha. Then Robert published a method of improved version aloha, improved version of aloha, snorted aloha, for doubling the capacity of the aloha system. By doubling the capacity, that means based on the pure aloha system, then the channel utilization of snorted aloha should be 36%, right? Should be 36%. So doubled 18%, 36%. So the snorted aloha will be 36%. So his proposal was to divide the time into discrete intervals called snorts. Each interval corresponding to 1 frame. This approach requires the user to agree on snorted boundaries. Oh, what is the snorted boundaries? Just now, we consider that during this period between T0 and T0 plus T, then the beginning of the frames probably begin to transmit it, right? In the period, then frames can be transmitted at any time between this period or this period. But if snorted time is assumed that only at the point of the beginning of this time slot, the frames can be transmitted. So the beginning of a frame only can rise at the -9 point, -9, at the beginning of the range, So this is the meaning of the time slot. So that is, the approach requires the users to agree on snort boundaries. Then the dotted line is the snort boundary, right? One way to achieve synchronization would be to have one special station emit a peep at the start of each interval, like a clock. So a station is not permitted to stand whenever the user types a 9. Instead, it is required to wait for the beginning of the next snort. Thus, the continuous time aloha is turned into a discrete time 1. This halves vulnerable period. Okay, the snorted version halves the vulnerable period. That means probably be collided. Vulnerable period halved, then utilization doubled, right? Halves the vulnerable period, then doubled channel utilization. That is the reason why snorted aloha can improve the performance. The probability of no other traffic during the same slot as our test frame is then E with the power of minus G, which leads to this utilization S equals G times E minus G. Right? So we can see from figure 3 here, right? Figure 3. So we know slotted aloha is better than pure aloha, right? Throughput is better than that of pure aloha. Especially when G is 1, then slotted aloha reach the maximum throughput. So the throughput of G is 1 over E, about 0.368. That is twice of the pure aloha. So it's nearly 37%. So the best we can hope for using slotted aloha is 37% of the slots empty. So that means 37% portion of the channel time successed, and only 26% conditions, right? So operating at a higher value of G reduces the number of empties, but increases the number of conditions exponentially. To say how this rapid growth of condition with G comes about, consider transmission of test frames. The probability that it will avoid the condition is this, which is the probability that all the other stations are silent in that slot. Okay, the expected number of transmission E line typed at a terminal is then E, denoted by E. Expected number of transmissions is E with the power of G. So as a result of the exponential dependence of E upon G, small increases in the channel node can drastically reduce its performance. So we know only when G at G equals 1, then the throughput reaches the performance. If the G becomes larger, then the increase becomes worse. Then we will talk about carrier sense multiple access protocols based on the pure aloha and the slotted aloha. With slotted aloha, the best channel utilization can now be achieved in 1 over E. With the stations transmitting at will without knowing what the other stations are doing, there are bound to be many conditions, because the protocol is very simple enough that without knowing what the other stations are doing, we don't know whether the other stations are transmitting or not. Transmitting at will, So the utilization cannot be very high. Many conditions, right? Due to many conditions. In local area network, however, it is often possible for stations to detect what other stations are doing, and thus adapt their behavior accordingly. So if the stations can detect other stations what other stations are doing, then the station can wait, right? Can wait until the channel becomes idle. Wait until the other stations finish transmitting the current frames. So it will help to induce it deduce the condition, right? So these networks can achieve a much better utilization than the basic pure Aloha performance. Protocols in which stations listen for a carrier and act accordingly are called carrier sense protocols. So if we add carrier sense characteristics to the Aloha protocol, then we can even improve the time snorted Aloha. So a number of them have been proposed, and they were long ago analyzed in detail. Have these other protocols with carrier sense. So carrier sense, time snorted, both can improve the performance. But sometimes time snorted scams cannot be realistic. But carrier sense, we can implement in the protocol. So when a station has data to send, it first listens to the channel. It first listens to the channel to see if anyone else is transmitting at that moment. If the channel is idle, the station sends its data immediately. Otherwise, if the channel is busy, the station just waits until it becomes idle. Then the station transmits a frame. If a collision occurs, the station waits a random amount of time and starts all over again. The protocol is called one persistent because the one means probability of one. Because the station transmits with a probability of one when it finds the channel idle. So if the channel is idle, then the protocol tells the station transmit the frame immediately with the probability of 1. If it is not 1 but 0.5 persistent, usually P persistent, then if the channel is idle, then the probability of transmitting a frame immediately is a half probability. That means with a half probability transmit and with another half probability not transmit. That is P persistent, non-persistent. Non-persistent is P persistent, right? So that's all for today. Thank you. Bye.